today's going to be better. Okay? There's not much you can do about a calculus review. Like, it's just going to be boring. Okay. Last time I started talking about what we're trying to get to is a way to represent position as a function of time. And I said in order to put numbers to position, you need to choose a zero position and a positive direction. You can't put numbers to anything without those. And so if you see a problem in the wild or whatever, like you're actually trying to solve a problem, the first thing you need to do is choose a zero position in a positive direction. If, on the other hand, you're given a problem that already has numbers assigned, that means that those two choices have already been made for you. There's no way to put numbers to position without it. Okay. And if we're trying to represent position as a function of time, we also need to choose a reference time. Okay? And so we need to choose an instant that corresponds to 0 time. So in order to define a function p of t, you need to choose 3 things. A 0, well, let me write it this way. A physical location corresponding to the 0 position. A positive direction. And an instant corresponding to 0 time. You don't have to choose a positive direction for time because time goes forward. It keeps on slipping into the future, slipping into the future. If the problem gives p versus t, or equivalently, it could just give a graph of position versus time. Well, so sorry, let me write this differently. So if the problem gives position as a function of time, or equivalently, a p versus t graph, those choices have already been made. Okay, so standard international units, I said for position, it's meters, or always some measure of length. For time, what are the SI units of time? Seconds, yep. All right, so here's an example where hopefully I can sort of bring out the relationship between these choices and the numbers that you get out of it. So let's say that, okay, here's you standing on the shore. Nice bathing suit. Here's the water. And out here somewhere there's a raft. And out a little farther there's a buoy. So let's say that it's 50 meters from the shore to the raft. And another 25 meters from the raft to the buoy. And let's say the swimmer starts on the shore at 1 p.m. You don't want to do this in the middle of the night. And reaches the raft at 1:02. The buoy at 1:03. And back to the raft at 1:05. Okay, so we're going to do this. What we're going to come up with is a position versus time graph for this motion, and we're going to do it with two sets of choices for those, those things that you have to specify. So first, let's say position equals 0 is at the shore. Positive direction is out to sea or whatever, out to the middle of the lake. And time equals 0 is at 1 p.m. Plot a position versus time graph in SI units. Okay, you do it. I'm bored of this. All right, so I think, to me, the easiest way to think about this is, so we'll put we said that the 0 position is at the shore, so I'm going to just label this point with the number 0. Positive direction is going this way. So if you go 50 meters in the positive direction from 0, then we can label that plus 50. If you go another 25 meters from 50, you get 75. And so he starts at 0, goes to 50 after 2 minutes, so 120 seconds. So the key positions are going to be 0, 50, and 75. At time equals 0, 1 o'clock, he starts at the position 0. After 2 minutes, he's at position 50. After 1 more minute, so that's at 180 seconds, he's at 75. And then it takes 2 minutes to get back to the raft. So that's what, 300? This is time in seconds. This is position in meters. And so we don't know exactly what is happening in between those points, but we know those points are like this. Okay. Anybody get anything different? Anybody go into the complex plane? Good. Yeah, there's no reason that this should give you complex numbers. Okay, so B, now let's do it again. Now we'll say if position equals 0 is at the raft, positive direction is towards the shore, so that switches. And let's say t equals 0 is at 12:59. do the same thing, plot the position versus time graph. Okay, so for this one, well, let me sort of sketch the situation again. So there's the shore, raft, buoy, and this time we're labeling the raft 0. The positive direction is this way. It's 50 meters between these two, so what's the numeric value for the position at the shore? Positive 50, because our positive is going, you know. And then what's the label for the buoy? Negative 25, yeah. And so the swimmer goes from 50 to 0 to negative 25 back to 0. This time we have to worry about the times a little bit more too. Well, I don't know if we really have to worry. We just have to deal with them. Okay, so this is position in meters. This is time in seconds. Okay, so we know that the swimmer starts at positive 50. How much time has elapsed since time equals 0 when the swimmer starts at the shore? How much? 1 minute, yes, because this time our 0 time is at 12:59. So the stopwatch goes, and then a minute of time runs by before the motion starts. So there's 60 seconds, and there's, I guess, the key labels for position are going to be, whoops, that should have been 50. 50, and then negative 25. And I'll just, so there's 2 minutes, 3, 4, 5, 6. Okay. So the swimmer starts at 50 at 60 seconds, gets to 0. Yeah.
Time 0, isn't he on the shore? Don't we have no point for 101?
Yeah, we don't really know. It just didn't say in the problem what he does before. I mean, he could have been walking from the snack bar or whatever. All we
It doesn't say he leaves at 101. It says at 1 o'clock exactly he's on the shore. At 1:02 he's at the raft.
That's right.
So you
But
don't know about what happened at 101.
okay, so this, but remember, this doesn't represent 101. This represents 60 seconds after our time equals 0. So this instant now represents 1 o'clock.
Oh.
Okay, because we have a different time equals 0.
Time t equals 0 at 12:59.
Right.
I didn't see that.
Okay. So then it's 2 minutes until the swimmer reaches the raft, and then 1 more minute till the swimmer reaches the buoy, and then he gets tired, and it's 2 more minutes until he reaches the raft. So the graph looks something like that. Okay, so the raft has done these things. It's shifted over to the right. What caused that? So basically, talking generally, we're making 3 choices. Which of those choices affects the left-right shift of the graph? Time equals 0. Which of those 3 affects the vertical shift of the graph? Position equals 0. And then which affects the flipping of the graph that happened? Positive direction. Yep, exactly. One thing to notice, this really is just a convention. There's no reason that, there's no mathematical reason that we wouldn't use negative times. Negative times would work perfectly well, but nobody does it. So let's just keep that in mind. We're not going to ever use negative times. Okay. in this class, we're going to deal with smooth position functions. P of t. Have you heard the term smooth before? Yep.
If we do use negative time, would we lose points? Or?
Yeah, don't do it.
Okay.
So smooth it's a descriptive term for one thing, right? Like if the graph is smooth, it doesn't have abrupt jumps. But it also has a real mathematical meaning. It means it's continuous and differentiable. And the reason we're going to use smooth functions is we're going to take derivatives from position to get to velocity and derivatives of velocity to get to acceleration. Okay. So for example, we'll deal with something like the position as a function of time is equal to 2t cubed minus 20. Okay. That's smooth because you can differentiate it. One thing to notice, I actually already said this today, but it's a key idea. Anytime you're given P of t, I might have said this in these exact words. Stupid! Okay. All right, anytime you're given P of t or a position versus time graph, it means P equals 0, positive direction, and 0 time have already been specified, have been chosen for you. All right, so the next idea we need to define is instantaneous velocity. The instantaneous velocity is also a function of time. You know, at different times you have different velocities. And it's just equal to the time derivative of the position function, which you can also write as p dot. Well, that's a pretty simple mathematical definition. So on a position versus time graph, how does the velocity appear on the graph? Like what physical property of the graph does this show? Yep, right. So the instantaneous velocity at a given instant is the slope of the curve at that corresponding time. All right, so for example, let's say that we have a function P of t is equal to negative 5t squared plus 5. So first, what's the velocity as a function of time? And second, what's the instantaneous velocity at the instant time equals 0.5 seconds? Okay, so do that one, please. I don't mean to be rude. All right, so this graph looks something like this. Starts at, so if this is position in meters, this is time in seconds. It starts out at 5 and is a parabola downwards that way. It crosses the 0 at 1 second. So half a second is here somewhere. And so the slope at that point, at that instant, is, you know, the slope of this tangent line. That's a negative slope. Excuse me. And doing the math, the function v of t is the time derivative of negative 5t squared plus 5, and so you get negative 10t. That's a function, so you could plot that, and sometimes we'll do that, although by far more common than velocity versus time graphs is position versus time. So that's part A, and then part B, you're just going to, you know, plug the value of 0.5 into this, and you get that the velocity at 0.5 is equal to negative 5. And this negative slope shows up there. The units of velocity are always length over time. And so in SI units, that's meters per second. So let's talk a little bit. Let me just describe how to physically interpret this value. So the physical meaning of the instantaneous velocity the magnitude is the object's speed at that instant. And the sign is the direction of motion of the object at that instant. So in this example that I just showed, what this says is that at time equals half a second, the object, we're talking about motion along a line, right? So the object can only be moving in the positive or negative direction. and at this instant, the object is moving in the negative direction. That's what that means. Okay. Physically, what direction does that mean? The negative direction? That depends on your choice of positive and negative direction. Okay, so let's go back to that swimmer example, and this time we'll use a function. Okay, so here's the swimmer, who his nose is different. He has tinier feet. But the raft's still there, the buoy's still there, and that distance is still 50 meters, and that distance is still 25 meters. And let's say that, well, the function, the position function is negative 0.00521. I just, chose values of these constants that made his motion about the same as it was before, so it would make sense with this picture. But times the quantity t minus 120 squared plus 75. So if you plot this motion, it's a parabola that starts at 0, 0 and gets back, I guess this time the swimmer gets back to the shore at 240 seconds. This is 120. So first, what's the velocity function? And this time plot a velocity versus time graph. Second, what direction is the swimmer moving at time equals make that 100, sorry. So what direction is the swimmer moving at time equals 100 seconds? And does that make physical sense with the problem? Well, in order to determine that, I guess I need to tell you that this function uses the fact that the 0 position is on the shore and the positive direction is this way. Okay, so you can orient yourself to the physical problem, relate the math to the physical problem with this choice of positive direction and this choice of 0 position. And then last, what direction is the swimmer moving at time equals 200 seconds? Actually, let's do one more. Is the swimmer ever at rest, and when? Okay, so go through that problem. And so v of t you can get by just taking the derivative. You get negative 0.01042 times t minus 120. And so, let's see. To plot this graph, so now if we're plotting velocity in meters per second versus time in seconds, what do you get? What's the value at time equals 0? You didn't do this, did you? Okay, thank you. I take it back. 1 point what? Okay, so let's say 1.25. And then it's going to hit velocity equals 0 at time equals 120, and then continue on. I guess it's symmetric, so it must have a velocity of negative 1.25 at 240. This is at 120 seconds. And this is a linear function. I asked for the velocity at time equals 100 and at time equals 200. Since this is the velocity versus time graph, we're looking at the values of these, not the slope anymore. So the instantaneous velocity is the slope on the position versus time, but the value on the velocity versus time. So what do you get for the values? Let's see. So for part B, the velocity at time equals 100 seconds. That should be positive. What do you get for that? 0.2084 meters per second. And so at that instant, what direction is the swimmer moving? Positive direction. And physically, what is that? Away from the shore. So does that make sense? If his turnaround point is at the buoy at 120 seconds, does it make sense that he's still moving away from the shore? Yeah. And then at 200 seconds, what's the value of the velocity? Negative 0.8336. Okay, meters per second. That's after the swimmer's reached the buoy and turned around. So now the swimmer's moving back towards the shore. What direction is that? Negative, and that makes sense with the sign we have here. Okay, so these answers make physical sense. What about, is there any point where the swimmer is at rest? Yeah, right at 120 at the turnaround point. If you look at the position versus time graph, right at that point you have a tangent line that has 0 slope. On the velocity versus time graph, it's where it crosses 0 velocity. How would you find that if you're asked to, I mean, I guess it's one thing if you're given, if you plot out the function, but mathematically, how would you find the instance where the velocity is equal to 0? Yep.
Where v of t equals 0?
Where v of t equals 0, so yeah, you'd set the first derivative of the position equal to 0, like when you're finding maxes and mins. Okay? It's a critical point. So v of 120 is equal to 0, and at that time the swimmer is instantaneously at rest. In the next instant, the swimmer's moving again, but just for that instant, you have no velocity. Okay, so now let's talk about instantaneous acceleration. The instantaneous acceleration is also a function of time, so that can change over time. There are a lot of cases where we're going to use constant acceleration, but it doesn't have to be the case. And it's equal to the time derivative of the velocity. And that means that it's also equal to the second time derivative of the position function. The easiest place to see this is on a velocity versus time graph, but like I said, we're not going to use those very often. On a velocity versus time graph, the instantaneous acceleration is the slope at the chosen instant. What we're going to use more often is position versus time graphs. And on a position versus time graph, if you have, so what is it? It's the second derivative. It's sort of related to the, what do you call that? There's a name for that, right? The concavity, right? So if you have a section of the graph that's concave up, that means that the acceleration is positive. And if you have a portion of the graph that's concave down, then on that interval, it means the acceleration is negative. So what about, speaking just like everyday speech, using acceleration the way we're used to just talking about it? You might look at this and guess that if you have positive acceleration, the object is speeding up, and if you have negative acceleration, the object's slowing down. It's a little more complicated than that. Okay, so whether the object's speeding up or slowing down is actually related to it depends on the relationship between the sign of the acceleration and the sign of the velocity. Okay, so don't make that mistake of thinking positive acceleration means speeding up and negative acceleration means slowing down. So I'll give you details on that in a second. Let me give you the SI units. So what do you think? Yep.
It's meters per second, or m over s squared.
That's right. Yep. So it's always going to be a unit of length over a unit of time squared. And so that's meters per second squared. And so it could be light years per years squared or light years per millisecond squared or whatever, as long as you have length over time squared. But this is the one we're going to use most. All right, so here's that key fact. This is so going to be on the lecture quiz next time. Okay? Who's listening right now? That's a lecture quiz question next time. So notice. One, for motion along a line, which is what we're talking about now, non-zero acceleration means the speed is changing. Okay, that's all acceleration can do. A lot of the things that we're talking about along a line are going to hold, or roughly hold, in 2 dimensions and 3 dimensions too. But this is one where it's pretty qualitatively different. In 2D and 3D, acceleration will also cause the object to turn. Although it can change the speed too. Second, whether the object is speeding up or slowing down. Depends on the signs of velocity and acceleration. If velocity and acceleration have the same sign, then the object is speeding up. If velocity and acceleration have opposite signs, then the object's slowing down. Okay, so think about it intuitively. What do you think? How would you describe a case where an object has a negative velocity and a positive acceleration? How would you describe what the object is doing? Yep.
It's getting closer to being at rest from moving in the negative direction.
Yeah, that's right. It's moving in the negative direction and slowing down. What if you have negative velocity and negative acceleration? What's it doing? It's moving in the negative direction and speeding up. Yep. Okay. I think maybe this will do it for today, but let's do one more example problem. All right, so let's say you have a position versus time graph. that looks like this. So it starts out with a linear region. And then it has like a parabolic region. So this right here is where you change functions. And I want to know over what interval is the object moving in the positive direction, same thing now, but negative direction for part B. Then for C, over what interval is the acceleration equal to 0? Over what interval is the acceleration positive? Over what interval is the acceleration negative? This is a lot of parts. Okay, two more. Over what interval is the object speeding up? And then over what interval is it slowing down? Over what region is it, over what interval is it moving in the positive direction? Yeah, right, until the second dotted line, so I guess I'll do it like this. So that's that red interval. When is it moving in the negative direction? Yeah, the rest of it. Is there an interval where the acceleration is equal to 0? So anytime, think about it, there's a couple ways to think about it. Well, first, it's the second derivative, right? So for there to be any acceleration, there has to be some concavity. Anytime you have a constant velocity, there's no acceleration. You know, acceleration is measuring a change in velocity, so any linear region is 0 acceleration. Okay? So this blue region is 0 acceleration. Is there any interval where you have positive acceleration? No, because there's no region where it's concave up. Is there any region where you have negative acceleration? Yeah, so all of the nonlinear part is a negative acceleration. I guess I'll write this in here. So there's no region with negative acceleration. Okay, so now speeding up and slowing down, we have to think about the sign of the velocity and the sign of the acceleration. Is there any region where it's speeding up? Yeah, the green, for that whole green region, you have negative acceleration and negative slope. And then, is there any region where it's slowing down? Yep, exactly. So in this region between these two, you have an acceleration that's down because it's concave down, and you have a positive slope. They have opposite signs, so it's slowing down. Exactly. All right. So that's it for today. Here's what we're going to go into next time. We're going to talk about going back and forth between the functions p of t, v of t, and acceleration a of t. I mean, we've already talked about how to go one direction, right? If we have the position function, take a derivative to get to velocity, take another derivative to get to acceleration. But we haven't yet talked about how to go in the other direction. What operation would you assume that you use? Yep, we're going to have to integrate to go in the other direction. But there's one little nuisance that comes up in going this way. And that's like the constants, exactly. So we have these unknown constants of integration that we're going to have to use physical things that we know about the problem to solve for. Okay? So that's what we'll do next time. Any questions? All right. So we don't have physics class on Tuesday. Everything gets sort of warped because of Martin Luther King Day. You're doing math on Tuesday instead. So the assignment I post today is going to be a double assignment. So don't skip it. And then we'll have class on Thursday, and then the second quiz will be on Friday. Okay? Have a nice weekend.